Okay, so next section we're going to talk about exponential functions. This will probably take us a couple days, today and tomorrow at least. We'll kind of see how it's going at that point. So exponential functions, I believe you did some with these in Algebra 2. So you guys just kind of have to tell me what you remember and how much I need to go through. So when I'm working examples, if you've got it and you're ready for me to move on, just tell me. So when we're looking at these, an exponential function is something of the form f of x equals a to an x. So the key here is the variable is in the exponent. A is just a number, so it's 2 to the x, 3 to the x, 1/2 to the x. That a is called your base, and your x, of course, is your exponent. So that's an exponential function. When we're going through these, is graph them. When we're graphing exponential functions, we use t-charts, but you really only had to plug in 3 points. Do you guys remember what 3 points you had to put in? 0 is one of them. 1 and -1. All right, let's try one. All right, so let's graph 2 to the x power. So if we put in -1, what does a negative exponent do? Flips it. So 2 to the -1 means 1 over 2, or 1/2. So -1 gives us 1/2. If you put in 0, what's anything to the 0 power? 1. If you put in 1, what's 2 to the first? 2. Is that enough? Do you guys remember what these look like? If not, we could put in more points, couldn't we? If I put in +2, what are you going to get out? What's 2 squared? 4. If I put in -2, it becomes 1 over 4. So -2 gives me 1/4. So it's this curve. Will you ever do 2 to a power and get 0 for an answer? No. So the x-axis is a horizontal asymptote here. So at a minimum, -1, 0, and 1 have to be the points you plug in. Could you tell me what's the domain of this? Negative infinity to positive infinity. What's our range?
0 to
And the 0 gets a parenthesis because we never actually equal 0. Is this function increasing or decreasing? Increasing the entire time. All right. What happens if I ask you to do 1/2 to the x power? So we know we have to plug in -1, 0, and 1. What is 1/2 to the -1? 2. Just flip it. So -1, 2. What's 1/2 to the 0? 1. Anything to the 0 power is 1. And 1/2 to the first is 1/2. So what changed? Same general shape. Really the difference is that in A it was increasing and B is decreasing. Domain. Range is still 0 to infinity. Let's do a few transformations with these. So we still have to do, we'll do a parent function and then any transformations that we might result. All right. What is my parent function going to be? By my parent function, I'm looking for just a regular exponential. So like 2 to the x, 1/2 to the x. In this case, it would be 3 to the x. So that's what I'm going to start with. All right, what is 3 to the -1 power? 1/3. So -1 gives us 1/3. What's 3 to the 0? 1. And 3 to the first is 3. So it's my parent function. I'm going to draw it as a dashed line. So transformation, what does that +1 do? Uh-huh. What does the -2 do? One thing that we need to watch on this, it currently has a horizontal asymptote at 0. If I go down 2, where's my horizontal asymptote now? -2. So on these, if you move up or down, you'll move your asymptote along with that. So I'm going to draw that in. So then I just have to take each of my points, left 1, down 2. What's my domain of range? Domain negative infinity to positive infinity. Range is -2 to infinity. -2 gets a parenthesis because we do not actually hit that value. All right. I want you guys to try. Parent function and transformation. So parent function, 3 to the x, that's the one that I expect the 3 points, -1, 0, and 1. So negative, when I put a -1, 3 to the -1 is 1/3. 3 to the 0 is 1, and 3 to the first is 3. So that's the parent. Does my horizontal asymptote move this time? No, that's only going to change if we move up or down. So we flip over the x-axis and right 4. So if I flip this, it comes down right 4. Flip that, it comes down to -1. right forward. Flip this one, so now it's 1, -3, right 4. So it looks like the same horizontal asymptote. What's the domain of this? What's the range? Do we need more of these graphs? Maybe one more. Half of you aren't answering me, so I think that means yes. If I said f of x equals 1/3 to the x plus 2. So what's our parent function? Yeah, the parent is just the number to the power. That's the one that you plug in your 3 points to start with. What is 1/3 to the -1? 3. 1/3 to the 0 is 1, and 1/3 to the first is 1/3. -1, 3, 0, 1, and 1, 1/3. Okay, what transformations do I have?
Up to, that's the only thing going on this one.
What's going to happen when I move my graph up to? The asymptote moves. So it was on the x-axis, so it gets moved up to +2. And then just take you to these other points up 2. Domain? Range? Two to infinity. Is this okay? All right, so the next piece that I want to get into is solving exponential equations. So equations that have exponents with variables. With this, we are going to use one key property. If you have the same base on each side in an equation, then that means the exponents have to be equal. So our goal is going to be so that we have like 2 to a power on each side, and then we can set those powers to be equal to one another. So I am going to do, I have a lot of these examples. This is really the one that you have to tell me if you remember doing this before or not. That'll kind of determine how many of these problems we work through. So let's take a look at this first one. 3 to the x plus 1 power equals 81. Now, could we guess and check and get an answer here? Absolutely. But some of these problems are going to get uglier. I might have variables on both sides, so they're going to get more challenging. So we need to figure out how to do it. Our goal is to get a common base on each side. Okay, I cannot change 3, so that has to stay. So the question is, 3 to what power equals 81? 3 to the 4. So now I have 3 to a power on each side. So the rule is you can just set those exponents equal to one another. So I could say that x plus 1 equals 4. Subtract our 1 and we get x equals 3. We can check them very, very easily. If I plug this in, I get 3 to the 4th, which is 81. So it does work out. Right. B. 2 to the negative x equals 16. So what would I do? Can't change 2, but I could rewrite 16 as 2 to the 4th power. So then these exponents are equal. Divide by negative 1, I get x to be negative 4. You guys remember doing anything like this? Okay. Let's do, I want to go ahead and do this next one. One-fifth to the x equals 1/25. There's a couple ways of doing this one. Any ideas? We could keep the base of 1/5. That's one option. 1 over 25 would be the same as 1/5 to what power? Just 2 actually, because 1 squared is 1 over 5 squared is 25. And then you get x equals 2. Another option, sometimes these fractions are a lot harder for people. So you could rewrite them without fractions. 1/5 would be the same as 5 to what power? Negative 1. A negative exponent flips it. 1/25. Let's just start for a moment. That's like 25 to the negative 1. So we have 5 to the negative x equals 25 is 5 squared. Two times negative 1 is negative 2. And we get to the same point. It was just a little bit longer to get there. So if you don't like fractions, you can flip them just by throwing in a negative exponent. We'll definitely look at a lot more of those. I'm going to skip D. I'm going to go to this one. What's different about that? We have variables on both sides. So this would be a problem where it's a lot harder to just guess and check. What else? Is 8 to some power equal to 16? No. So we're going to have to change both sides. They're both, 8 and 16 are both powers of 2. You need to be very careful when you go about writing this so you don't confuse yourself. 8 is 2 to the 3rd power. I am putting that in parentheses and negative x plus 14 on the outside. Why? Yes, we're going to have to distribute that through. 16 is 2 to the 4th to the x. So when we multiply power to a power, we're going to multiply those. So we get 2 to the negative 3x minus 42 equals 2 to the 4x. Now I have the same base on each side. So now I can set my exponents equal. Is everybody okay with how I got to this point? So if I add over my 3x, divide by 7, and I get negative 6. Hold on. I changed my positive to a negative, didn't I? That was a positive 14. So it should be positive 6 at the end. I'm only going to do a couple more for today, so let's try and get through just a couple. F. This is the type of problem where the most mistakes are made. And it happens from people dropping the base too soon. When I look at the left-hand side, I have the base of 5 written twice. When you're multiplying and that base is written each time, what do you do with your exponents? Add them. So I need to combine this first, and I'm going to add those exponents. So that's 3x minus 2. On this side, my base is 1/5. How could I change that? To the negative 1. Equals negative x minus 4. Add over my x. Add over my 2. Divide and we get negative 1. So you just have to remember, you cannot drop your base until it's only written once on each side. If you drop it too soon, you end up multiplying those exponents, and that's going to give you the wrong answer. How comfortable are you with these? I don't know if you just spent a little bit of time on them last year, or if you had a lot. Do you guys really remember? Let's do one more, and this is my last problem for today. Let's do I don't want to do that. Sorry, I'm trying to decide. I wanted a hard one. Let's do this one. So this one sometimes throws people because of the base. It's an E. What is E? It's a number. It's kind of like pi. Okay, it has a set value. It's 2.718 and just keeps going forever. Does that matter in solving this problem? No. My base is the same on each side, so what do? Set the exponents equal. Alright, so if I subtract over my 3x, divide by -2 and we get -4. Alright, I'm not done with this. We're going to do some more tomorrow, but I want to go ahead and give you guys some problems. So if you will look, there's a handout posted on Classroom. Technically, you could do 1 through 16 on this handout. I am not collecting it tomorrow, but I am going to give you more homework. Okay, so I would recommend trying those first 16 problems. We haven't done tons of examples, so if you're struggling with